Chapter 10 Radioactivity. In 1896, a French scientist, Henri Becquerel, observed that when a metallic object was placed between a photographic plate wrapped in a black paper and a crystal of uranium compound, an image of the object was formed. Since the black paper was opaque, he concluded that the radiations which penetrated the paper must have emanated from the uranium compound. Other scientists, Marie Curie and her husband Pierre Curie, carried out related investigations from which they concluded that the radiations originated from the nucleus, and they called this phenomenon radioactivity. Nuclear stability. The nucleus of an atom has a specific number of protons and neutrons. The number of protons in the nucleus is called the atomic number, while the sum of the number of protons and neutrons is called the mass number. If an atom X has atomic number Z with n neutrons and mass number A, it can be represented as shown here, where A is equal to Z plus n. Stable nuclides have proton-to-neutron ratio of about 1:1. However, as atoms get heavier, there is a marked deviation from this ratio, with the number of neutrons far superseding that of protons. In such circumstances, the nucleus is likely to be unstable. When this happens, the nucleus is likely to disintegrate in an attempt to achieve stability. This graph shows the number of neutrons n against the number of protons for non-stable and unstable nuclides. From the graph, it is observed that the unstable nuclides are outside the stability line. Those nuclides above the stability line have too many neutrons, hence decay in such a way that the proton number increases. Those below the stability line have too many protons and therefore decay in such a way that their proton number decreases. In either of the cases, radiations are emitted. The British scientist Ernst Rutherford was one of the first to show that radioactivity could consist of three distinct types of radiations. The three differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed to a fluorescent screen which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into three components. One of these is deflected upwards by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downwards, indicating that it is positively charged. These radioactive emissions are called alpha rays. Note that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiations. The portion of the original beam that is undeflected is due to radiations that is not charged and are called gamma rays. So, radioactivity is the spontaneous random emission of particles from the nucleus of an unstable nuclide. The process of radioactivity is not affected by such external factors as temperature, pressure, or chemical composition. When a nuclide emits the radiation, it is said to undergo radioactive decay. During radioactive decay, the nuclide will emit alpha or beta particles, and this may be accompanied by a release of energy in form of gamma radiations. Alpha decay. Alpha decay occurs when an unstable isotope gains stability by losing a whole nuclide. An alpha particle is basically a helium nucleus represented as shown here. So if a nuclide decays by release of an alpha particle, the mass number decreases by 4 and the atomic number by 2. So if a parent nuclide X with mass number A and atomic number Z undergoes an alpha decay, we shall have a daughter nuclide Y with mass number reduced by 4, that is A minus 4, and atomic number by 2, Z minus 2, plus an alpha particle which is essentially a helium nucleus. Notice that the daughter nuclide is completely different from the parent. To identify the daughter nuclide, we simply check the new atomic number from the periodic table. For example, polonium undergoes alpha decay to form lead as shown here. Now for an example. If uranium-238 undergoes a single alpha decay, what element will be formed? In the solution, we write the equation uranium-238 undergoing alpha decay. Mass number reduces by 4 to give 234. Atomic number reduces by 2 to get to 90. From the periodic table, that new atomic number 90 is thorium. Beta decay. An unstable nuclide may also gain stability by conversion of a neutron into a proton. Consequently, an electron is emitted. This is beta decay. So a beta particle is basically a high-speed electron resulting from the conversion of a neutron to a proton and is represented as shown here. And so if a nuclide undergoes beta decay, the mass number remains unchanged, but the atomic number increases by 1. For example, radioactive sodium undergoes beta decay to become magnesium. Gamma rays are not particles, but rather are electromagnetic radiations that usually accompany the emission of alpha or beta particles. Some nuclides might be in an excited state, and to achieve stability, they may emit energy in form of gamma radiation without producing new isotopes. For example, cobalt-60 and thorium-230. Sometimes, a radioactive decay may result in a new nuclide, which is also unstable. The daughter nuclide will thus undergo another decay until a stable isotope is obtained. This is called a decay series. For instance, thorium-232 is unstable. It undergoes alpha decay to form radium-228. Radium-228 is also unstable and undergoes a beta decay to form actinium-228. Actinium-228 is unstable as well. It undergoes a beta decay to form thorium-228. Thorium-228 is also unstable. It undergoes an alpha decay to form radium-224. Radium-224 is also an unstable isotope. It undergoes yet another alpha decay to form radon-220. This decay series continues until we get a stable nuclide, lead-208. From this series, you notice that two similar particles can be released in succession to form a new nuclide. For instance, radium-228 undergoes two successive beta decays to form thorium-228. This equation can be summarized as shown on your screen. Thorium-228 undergoes 2 successive alpha decays to form radon-220. These can be written as shown on your screen. Penetration power. The 3 radioactive emissions have different penetration powers. Alpha particles are the weakest. They travel slowly through air and are stopped by a sheet of paper. Beta particles are stronger. They penetrate paper but are stopped by a piece of aluminum foil. Gamma rays have the highest penetration. They penetrate paper and aluminum foil and are only stopped by a thick lead block. Radiation detectors. The cloud chamber. When air is cooled until vapor it contains reaches saturation, it is possible to cool it further without condensation occurring. Under these conditions, the vapor is said to be supersaturated. Gaseous ions can act as nuclei for condensation. The ionization of air molecules by radiations is investigated by a cloud chamber. The common types of cloud chambers are expansion and diffusion cloud chambers. In both types, saturated water or alcohol vapor is made to condense on air ions caused by radiations. Whitish lines of tiny liquid droplets show up as tracks when illuminated. Next is the Geiger-Müller tube. The Geiger-Müller or GM counters are one of the gas-filled radiation detectors that operate by using the ionizing nature of the alpha, beta and gamma radiations. The GM tube is a sealed metal cylinder containing a low-pressure inert gas such as argon or neon. A thin metal wire runs down the center of the tube, which is electrically insulated from the outer cylinder at the rear end. The front of the tube is sealed with a radiation window that is specific to the typical radiation to be detected by the counter. For example, a thin mica window is used if the tube is to be sensitive to alpha particles, which have low penetration power. A thicker window such as glass or a sheet of metal is used for high-energy beat particles, while for gamma rays, the tube is often sealed without a window. In such tubes, the detection occurs when the high-energy photons liberate electrons from the tube's outer wall. Incoming radiation ionizes some of the inert detector gas, resulting in a free electron and a positively charged ion. The electric field inside the tube attracts the ion to the outer cathode and the electron to the central anode. As the electron approaches the anode, the electric field and the counters grow in strength, so the accelerating force increases. Near the anode, the acceleration is such that the electron has enough energy to either excite the electrons in the other atoms of the gas or to ionize them completely. Excited electrons quickly decay, releasing photons that can trigger ionization further along the tube, while electrons freed by ionization can go on to cause further ionization, leading to an exponential growth. This is called the avalanche effect. The charge migration in the tube leads to a reduction in the potential of the anode and an increase in the potential of the cathode, either of which may be detected as a signal by the detector of the electronics. Artificial radioactivity. Some naturally occurring nuclides can be made artificially radioactive by bombarding them with neutrons, protons, or alpha particles. For example, when nitrogen-14 nuclide, which is stable, is bombarded with fast-moving alpha particles, radioactive oxygen is formed. Other artificially radioactive nuclides include silicon-27, sulfur-35, and chlorine-36. Decay law. Radioactive decay is a spontaneous random process in which one cannot point out the nuclide that will disintegrate next. The choice of the nuclide that decays is governed by chance. This is because extremely large number of atoms is usually involved. The decay law states that the rate of disintegration at a given time is directly proportional to the number of nuclides present at that time. This can be represented as dN over dt is proportional to negative n, where n is the number of nuclides present at a given time. It follows that dN over dt is equal to negative lambda n, where lambda is a constant known as the decay constant. The negative sign is used to show that the number n decreases as time increases. dN over dt is referred to as the activity of the sample. Half-life. The rate of decay of any radioactive material depends on the number of nuclides present. The time taken for half the number of nuclides initially present in a radioactive sample to decay is called its half-life. Consider 4 grams of radium whose half-life is 1,600 years. After 1,600 years, 2 grams will have decayed, so we shall have remained with 2 grams. After another 1,600 years, half of the 2 grams will decay, so we shall remain with 1 gram. Another 1,600 years, and half of 1 gram decays, so we remain with 0.5 grams, and so on and so on. This can also be given in form of percentage. Initial amount is always equal to 100%. Mathematically, if n0 is the original amount of a sample, n the number of half-lives, then the remaining amount n is given by n is equal to n0 times a half raised to n. For example, if we have 8 grams of radium whose half-life is 1,600 years, how much will be remaining after 6,400 years? Our formula n is equal to n0 times a half raised to n. First we calculate n, the number of half-lives. One half-life is 1,600 years, so 6,400 years is equal to 4 half-lives. That is simply 6,400 divided by 1,600. So n is equal to 8 into a half raised to 4. N is equal to 8 times 1 over 16, which is equal to 0.5 grams. This is the amount that will be remaining after 6,400 years. Now, this technique is used in radiocarbon dating, using carbon-14 to estimate the age of fossils. For example, An excavated skull is found to have the activity of carbon-14 of 12.5%. If carbon-14 has a half-life of 5,600 years, find the age of the skull. This time we have our amount in percentage. Original activity or amount is equal to 100%, always. Final activity or amount is equal to 12.5% that we are given. Half-life is equal to 5,600 years. So what we need is the number of half-lives. Once we get it, because one half-life is 5,600 years, all we will need to do is multiply to get the age. So n is equal to n naught times a half raised to n. 12.5 is equal to 100 times a half raised to n. We divide both sides by 100, so we shall have 0.125 is equal to a half raised to n. I love to work with decimals, so a half is the same as 0.5. So we have 0.5 raised to n is equal to 0.125. Put your best mathematics. Introduce logs. N log 0.5 is equal to log 0.125. To remain with n, we divide both sides by log 0.5. If we do that, n is equal to 16. So there are 16 half-lives. Each half-life is 5,600 years. So how many years are those in total? We simply multiply, and if we do that, we get 89,600 years. That is the age of the skull. Nuclear fission. In 1939, a German scientist, Otto Hahn, discovered that breaking up the nucleus of uranium-235 into two parts emits 200 million times the energy of the neutron which triggered it. A process in which heavy nuclei are bombarded with neutrons and split into two equal masses, releasing enormous amount of energy, is called nuclear fission. When the nucleus of uranium-235 is bombarded with neutrons, it absorbs one of the neutrons, thus forming a highly unstable compound nucleus, uranium-236. This is what triggers the nuclear reaction. During the process of fission, uranium-236 splits into two product nuclei, which are barium-141 and krypton-92. The unstable uranium-236 nucleus also releases 3 neutrons in the process. The nuclear equation for the reaction is shown here. These neutrons can be absorbed by other uranium-235 nuclei, resulting in a chain reaction. This leads to exponentially high amount of energy being released by a single reaction. Nuclear fusion. Nuclear fusion is the nuclear reaction in which lighter nuclei are combined together to form heavier product nuclei with the release of enormous amount of energy.